I wish you all a warm welcome. I'm Nagarajan from Lumentum, and the title of my talk is Extending the OpenROADM to the Network Edge. And as the title suggests, a bulk of the presentation is going to be on the work that we were doing in the OpenROADM forum, trying to bring optical specifications that are targeted towards the edge of the network. And as part of this conversation and the topics, I will introduce what the concept of an edge is, and I'll also talk a little bit about the elasticity between cost and feature set that will allow more economical solutions for the edge of the optical network. And then as a thought experiment towards the end, I would look at the concept of a node on a blade as opposed to a degree on a blade and look at what it does to system MTBF. So let's start with the definition of what I mean by the edge of the network. So the edge of the network is that part of the wide infrastructure where the traffic pattern is mainly north-south. There is very little east-west traffic between the nodes that form the edge, and bulk of the traffic in this part of the network is kind of like a hub to spoke. Now, with the advent of 5G services, content caching, and edge computing, the edge of the network is seeing a plenty of unplanned traffic growth. Now, we know from history that a ROADM-based network works very well when the traffic patterns are unpredictable. But the ROADM economics, which are currently optimized for metro solutions, simply do not price in at the edge of the network. And this part of the network is mainly served by fixed optical add-drop filter-based structures. Now let's look at the application drivers for developing an edge ROADM specifications. And as mentioned before, a fixed OADM rings are historically used for the access aggregation rings. Now, while a FORDM-based network does give you the advantage of a lower cost, as long as you have an a priori knowledge on how the traffic patterns are going to grow. If the network growth pattern is unpredictable, a FORDM-based network becomes operationally very complex. Another change that's happening in the overall networks is coherent DCO modules are finding ubiquitous applications in all parts of the network, including the edge. And if you're going to be using coherent ports at the edge of the networks, it is desirable that any wavelength that originates at the edge of the network should be transparently routed into the metro core. A FORDM-based ring cannot support transparent wavelength routing to the metro without creating a stranded bandwidth. Now, these 2 points do make a strong case for a lower cost edge ROADM that is transparently able to interact with the metro core. Now let's look at from an OpenROADM architecture perspective, the fundamental differences at the high level between what is a metro network and what is an edge network. Now, if you look at the definitions of a metro network, typically we expect it to have between 8 to 16 degrees at any given nodal site. The ROADM architecture is also going to be route and select, and it'll be a full flexible grid operation. And on the add-drop side, you're looking at either a CD or a CDC, that is colorless directionless, or colorless, directionless, and contentionless. But colorless and directionless is absolutely mandated. Now, if you were to look at what is the corresponding thing that has been proposed and accepted for the edge, is we're looking at the edge requiring somewhere between 2 to 4 degrees. A broadcast and select type of ROADM architecture is accepted because the edge has to transparently interoperate with the metro. The edge is also mandated to have a full flexible grid operation. And on the add-drop side, we are looking at either colorless and directioned, or colorless with directionless capability as well. So, but colorless is the most important aspect of it, and the rest of the add-drop, it could be direction, it doesn't matter. So what does that allow you to do? It, at least from a higher level, it allows you to look at network solutions that are dimensioned at a much lower degree of complexity than what is required for a metro ROADM type application. In the previous slide, we talked about broadcast and select and route and select type ROADM architectures. So let's take a look at in more detail what these different ROADM approaches are. In a route and select type of an application space, you typically would deploy a twin WSS on a per degree, and you'll have a WSS for both the MUX and the DMUX side. And if you look at a blade type implementation, you're going to have the preamp and the booster amplifiers built in along with the blade. And if you've got, say, like a 4-degree node, you're going to have 4 of these blades deployed in that particular site. Now, this is a very feature-rich type design architecture. It also enables a CDC on the add drop, also provides path level redundancy. And because it's feature-rich, its cost is also relatively high. Another approach that's often used for smaller nodes is called as broadcast and select. Here on the DMUX side, as the traffic comes in, you use a passive splitter to split out the signals, and then for the add side, you have a single WSS. Now, compared to a route and select, this is relatively cheaper. It also enables colorless or colorless directionless type architectures on the add drop. And if you're going to be using separate blades for each degree, you'll get the path level redundancy you need. And compared to like a route and select, the cost points are definitely much lower. Now, a third approach that is just gaining a little bit of traction among the operators with recent RFQs and RFIs that are coming in is instead of looking at degree on a blade, you're trying to look at an entire node on a blade. And when I say node on a blade, typically it's more like a 2 degrees on a blade. Now that can be implemented by using a single twin WSS as you have in the case of a route and select. But instead of using a route and select, you in fact use each half of the twin for each degree and use couplers for the DMUX side. And just like before, you would need an equivalent complement of preamplifiers and boosters on a given card. So this is definitely more cost effective than any of the other two approaches shown, and it also enables colorless and directionless, but it also has there is a caveat that it also is a single point of failure. So if this one blade goes, you're going to lose both the east and west direction, but the cost points are much lower. And in the case of an edge, this might also be quite a cost economic choice. Now let's look at the node level reference model for both the edge and for the metro as defined in the OpenROADM MSA specification version 5.0. And as you look at the two reference models, the first thing that is very apparent compared to a traditional metro application is that the edge is actually showing a broadcast and select type architecture here. And at the same time, on the add drop side, you could see that it supports the colorless, but each wavelength path is routed to a given direction. So it's colorless and direction. Whereas in the case of the OpenROADM Metro, which has to support colorless and directionless, you could see there's an additional switching element here that allows each and every wavelength path to take either direction to provide you both the colorless and the directionless aspect of it. So now let's get a little bit more into the details in terms of the key specification differences between what has been proposed in the OpenROADM for the metro portion versus what's there currently that we have broadly accepted for the edge application space. As mentioned before, I mean, in terms of the node architecture, we said, okay, we also support in the edge broadcast and select in addition to the route and select. That's already part of the metro standards. And the other one is in terms of the dimension of a node, the edge is dimensioned for between 2 to 4 degrees support, whereas the metro's dimension for an 8 to 16 degree. The other crucial difference is that the metro has to support 0 to 30 dB span loss. And for the edge, given that links are going to be small and to reduce the burden on the amplifiers, we truncated the span loss requirements from 0 to 20 dB. Now, given that they have to do a transparent optical handoff between the edge and the metro, it is 4.8 terahertz spectral occupancy for both. The next two are crucial in terms of the differences, and they relate to the control loop speeds. In the current OpenROADM metro specifications, the amount of time allocated for a channel to achieve its target power is around 12 seconds. That is assuming you have 96 channels that are not provisioned, and you bring 96 channels up, you are given around 12 seconds. In the case of a metro, we have relaxed that, in the case of the edge, you relax that to about 80 seconds for all channels. And again, for in-service channel changes is 8 seconds for the metro, and you've relaxed it to 40 seconds. And the reason for doing that is that it allows us to build solutions with embedded optical channel models inside WSSs to reduce the overall system cost. So what do we get at the end of the day? The broadcast and selected architecture of the edge gives us lower cost. The lower span losses gives us simplifies the amplifier designs for the edge, and a slower power control at the edge enables a much lower integrated OCM approaches. So I've taken some important graphs from the OpenROADM MSA version 5.0 document. One of them is on the launch power mask, and the other is on the incremental OSNR mask for a given node. Now, and I have superimposed or laid them one on top of each other, one for the metro case that's there, and the other for the edge, just to highlight the differences that are there between the two. Now, in the case of a metro, you're supposed to go and allow for span losses that goes from all the way 0 to 30. And you can see that the green line here is the launch power mask, and this is a launch. And when I say launch power, it's actually the power spectral density on a 50 gigahertz window. And as the span losses increase, eventually it caps off at around 2 dBm per 50 gigahertz power into the fiber in the case of a metro link. In the case of an edge, the cap on the output launch power is given at 0 dBm for a 50 gigahertz power spectral density, and the reason for that it's done is again to reduce the burden on the amplifiers. So as far as the slope goes in terms of the launch power mask, as long as you're going from 0 to 17 dB, both the graphs are identical in terms of the launch power power mask. But once you hit around the 17 dB, the edge plateaus at 0 dBm, whereas the metro continues to rise until it hits around the 22 dB mark, and then it kind of plateaus there at 2 dBm. So that's one of the differences in terms of the specifications of launch power masks between the two. And then the two graphs on the right, they talk about the incremental OSNR as you traverse from one span to node to the next. Now, in the case of the edge, you're supposed to have the power spectral, the spans going all the way down to 30 dB. And in the case of the edge, we are going to go only up to 20 dB. So that's why the portion that is there from minus 25 to 20 dB is grayed out. What you can see from here, there's actually no difference in terms of the incremental OSNR mask. So whatever the incremental OSNR mask that you have accepted for the metro, the edge has to cater to the same masks, except that it is not defined for number for values of span losses more than 20 dB. And this is done primarily so that when you do any link engineering rules for the metro and you want to extend that to the edge, you're dealing at least with the same numbers, and the problem is fairly simplified. So we talked about how some of the specifications in the metro OpenROADM specs were relaxed in order to generate the edge specifications. Now, the fundamental purpose of all of this is to reduce the boundary conditions and make the problem dimensions in such a way that one can come up with economical solutions for the edge. So let's put some numbers to that. And what you see here in terms of the leftmost candle is the typical cost of a Metro ROADM degree, fully featured, can do 6 to 16 degrees, can do 30 dB spans with a separate preamp booster, no standalone OCM, and everything like that. Now, once we did do a relaxation on the amplifier spec, which basically means reduce the span loss to about 20 dB and reduce output, cap the output power at 0 dBm per 50 gigahertz spectral occupancy, we can reduce the cost of a degree by about, I would say, 75% from where you started out with. And now then, if you take in the other feature relaxation that was done, wherein we relaxed the timing requirements on the optical channel monitor, we further reduced the solution cost to around 60% of where you started out with. And then if you take the next degree of freedom, and again, it is not mandated by OpenROADM, but it is again one of the degrees of freedom one can use, is instead of building degree on a blade, one builds a node on a blade to get some more cost reduction. One can come up with cost points for the edge that are around 45% of what you would pay for a regular Metro ROADM blade degree. So let's take a look at the Yang model additions that are required to support the edge ROADM. Now, in terms of ROADM nodes in OpenROADM, now we have two different types of ROADM nodes. One is for the Metro, and other one is for the edge. And the SDN controller needs to have a mechanism to distinguish which node type it's dealing with, as the specifications for both node types are slightly different. So we defined a new node subtype just to articulate the differences between the two. And again, it's a type of an enumeration. And then and when you query that for the node subtype, and in case it returns a none value, then the assumption for the SDN controller is that it's dealing with the standard Metro ROADM node, and all the standard OpenROADM properties apply in that case. But when the node subtype is queried and it returns an enum that says edge optical spec, then we know that those optical specifications that as apply to the edge for the MW to MW edge, MW to WR edge, and the local control edge will apply to that particular node. The next few slides are not directly related to OpenROADM, but they are related to solutions that are low cost towards the edge of the network. Now, one of the theses that we put forward at one particular point in time is solutions could be looking at a node on a blade as opposed to looking at an individual degrees on a blade. And historically, that has never been done simply because the system reliability and the MTBF numbers and system availability numbers don't seem to work out. So we decided to do an academic exercise on looking at what the real world data of blades are, and then come up with the concept of a node on a blade and see what the availability numbers look like. So the picture on the left here shows the traditional method of building a ROADM degree. So each degree is built out of an individual blade. So if you've got a 4-degree node, you got to have 4 of these different blades. And when we look at what the fit numbers are based on 10 years of field data based on Telecordia method 3, we roughly come to around a fit of about 1,000 for a ROADM blade. That includes the amplifiers and the WSS. So in a solution like this, if 1 degree fails, the traffic can still be routed through the other degree. And if you were to make an integrated card, wherein both the degrees are on the same blade, you'll expect to get a fit of around 1,200 because of the additional electronic components required that need to be fit onto the blade. So now let's look at a 4-node edge ring built with 2 different solutions. The solution that you see on the left is the traditional way of doing it, wherein if you have a 2-degree node, you're going to have 2 separate blades for each degree. and as depicted by the green squares here. And the picture at the bottom here shows the concept if the 2 degrees were integrated onto a single blade. So if you look at the node number 4, if this blade were to fail, then you're going to lose both east and west. And here, of course, if this particular one of these blades fail, you still have the ability to route the traffic through the other blade. So what we did is we decided to crunch down the numbers. So we looked at the MTBF numbers for each of these nodes from node 1, 2, 3, and 4, assuming that if each one of these nodes fail, what does the overall system availability numbers look like? And the results that we got were kind of surprising. So I mean, again, let's assume that there's a service life of around 15 years, and then the mean time to repair is around 24 hours. What we found is only for those nodes that are closest to the metro edge, which is either node 1 or node 4, the degree separated solution gave a much lower fit number or a much higher mean time to failure number compared to an integrated solution. But once you move away from the edge, that is, you go to nodes number 3, 2, 3, and 2, and in case there's a 5 node, say node number 5, we find that the availability numbers or the failure fit numbers between whether it's an integrated solution or a degree separated solution come out to be the same. So what we find, at least from this experiment or from this calculations, is that at least for the edge applications, going with a node on a blade is actually not a bad idea. In fact, the numbers do pan out. Now, there might be other reasons why an operator may not choose to do a node on a blade, but it's definitely not based on the network availability numbers, at least because, at least as far as we see, the data goes, the data does support a concept of a node on a blade for edge type applications. So in summary, I would say that ROADM solutions for the edge are required to replace the current FORDM-based solutions. And that is because the traffic patterns are becoming more unpredictable and coherent ports are making their way towards the edge. The OpenROADM forum work has shown that architectural simplifications allow us to design low-cost solutions towards the edge, as the economics absolutely need to work for the ROADMs to be deployed. The other activity that also showed to us is a single point of failure type of an architecture, wherein as opposed to a degree on a blade, you design a node on a blade, is a valuable architecture alternate to achieve low cost. And some of the analysis that we have shown in this presentation does suggest that a single point of failure design does not introduce significant impact on system availability numbers. I thank you all for listening to this talk.